This video is going to explain the three types of standing waves that we're going to be dealing with here in IB Physics. The first is a transverse standing wave with strings fixed at both ends. There's different possibilities you can get when you get a standing wave on a string. The first, is this guy with just one little bump here. If I drew it out, like this, it would just look like this with look like half a wavelength. All right. And what we see is that the length is equal to half a wavelength. I'm going to define the length of this string 6 meters. I'm going to say that the speed of the wave on the string is 1200 meters per second. That's determined by the density in the bulk modulus of, the tension in the bulk modulus of the material. All right. In this case, since we got the wave speed determined by the medium and the wavelength of the wave, we end up being able to solve for the frequency of that wave, which is just going to be 1200 meters per second divided by 12 meters. Now, how did I get 12 meters for the wavelength? Well, since this is just half a wavelength right here, and the length of the string is 6 meters, to get a full wavelength, we'd have to keep going, and it would have to be 12 meters. Okay? So that's how we know that that wavelength of that standing wave is 12 meters right there. And we solve for the frequency that this string must be vibrating at to create this form, and it's going to be 100 hertz. So let's create a different type of wave. You saw me, I created in class a couple of different examples of standing waves, one with one bump as I was describing it, this one with 2 bumps. Okay, we have this drawing over here that shows what that would look like. Okay, and we see that the length of the string is the wavelength. We call it wavelength 2. This is the second example, okay, or the second resonant frequency, what we'll be calling it. So lambda is equal to 6 meters, solve for the frequency we see is 200 hertz. You'll see that that's 2 times the original frequency, the fundamental frequency, which is what we'll call it. All right? That has to be a higher frequency for that shape to occur. To get this shape where we have 3 bumps, again, the drawing I have over here, okay, the length will look like, 3 halves, it gets 3 halves of a wavelength, lambda 3 we'll call it. The wavelength itself is just 2/3 the length. All right, so the wavelength I solve for down here is 4 meters, right? And then I solve for the frequency, and I substitute lambda in there, and it has still the same wave speed, and I get 300 hertz. So we see that the frequency has gone up by another integer multiple of the fundamental frequency, okay? So what we have here, all right, is a little bit of a pattern. And so just a general description of the boundary conditions at the end of both these, at the end, 2 ends of this string, they're both fixed, so we have a node at each end. It's very important to note right there. All right. What we get are different harmonics. Those harmonics refer to different waveforms based on different frequencies. The fundamental harmonic, the first harmonic, creates a waveform where the length of the string is half a wavelength. Okay. If we substitute that into our wave equation with lambda 1 equaling 2L, we get the fundamental frequency is equal to V divided by 2L. To solve for the other possible frequencies, we notice that they went up by integer multiples. So to get the other fundamental frequencies, we multiply, to get the other harmonic frequencies, we multiply the fundamental frequency by n, where n is any integer, okay? And this is our general equation to solve for the frequencies, of a string fixed at 2 ends. We got a couple more examples here. The next example is a longitudinal standing wave, a pipe that's open at both ends. Okay? If we have a pipe open at both ends, we end up with the displacement of the air, okay, looking something like this, all right, where we have antinodes at both ends, okay, of our pipe. Now, those are antinodes for displacement. Okay, the displacement of the individual particles have antinodes at both ends. All right. If we're looking at the pressure variation, however, okay, it looks a little bit different. The pressure variation, okay, the displacement of those of the individual particles is an antinode, okay, but the pressure variation looks very, very different, where we have nodes on the pressure at both ends and an antinode in the middle. Okay, we'll talk about why that is in class, so we'll do a demonstration next time that I see you. Okay, but again, this is air that's moving through this tube. Okay, it's the speed of sound in air. So we have 340 meters per second is the speed of the wave in the medium. Here we see from our drawing that the length is going to be 1/2 lambda, okay? We have half of a wavelength in there. So the wavelength itself is 2 times the length of the tube. I've decided that the tube is 0.6 meters long and just established that ahead of time. All right. So if you solve for the first harmonic frequency, we end up with 340 meters per second divided by 1.2 meters, 283 hertz. Okay. Moving on here, okay, the next possible situation where we have antinodes for the displacement of the particles at both ends, okay, free open ends here in the tube, we end up with this waveform, which is just one wavelength. So we see that the length of the wave is just lambda itself, all right? This lambda is equal to 0.6 meters, solve for the frequency. And again, we see 567 hertz with rounding here, okay, because this is 283.33, this is 566.666. It's double the fundamental frequency. Okay, so we see that this is kind of an analog. The two free ends in a pipe is an analog to the two fixed ends of the string. We get to the same thing here with the next harmonic. Okay, the length is going to be like this, 3/2 times lambda 3. Okay, so we see that lambda is just 2/3 the length of this tube. And when we solve for the fundamental frequency, we see that it's 800 and I believe it would be 49 hertz, which is going to be 3 times, all right, actually 850 hertz, right, 3 times the fundamental frequency, all right? So the boundary conditions here are that we have two free ends. In other words, we have two antinodes at each end. That's what we want to talk about there when it says the displacement nodes, okay? So the displacement nodes are at the displacement nodes, you have maximum displacement, you're at your amplitude at either end, at the free ends, okay? So maximum displacement. The amplitude. All right, so the fundamental frequency can be determined, all right, when the length is equal to 1/2 lambda. Okay, we solve for the fundamental frequency using the same equation as before. Other natural frequencies, again, follows the same pattern. Multiplying the fundamental frequency by an integer each time will give you the next set of resonant frequencies. Okay? So finally, get to this third example. And with this third example, what we have is a longitudinal wave where we have one pipe that's open and the other pipe that is closed. Okay? The other end of the pipe that is closed, excuse me. So when you have this situation, okay, you have something that looks like this for the displacement nodes. You have a displacement node, the displacement here is equal to 0. Right? And the displacement here is equal to x naught, the maximum, or the amplitude, okay? So here, this waveform right here is only 1/4 of a wavelength for the entire length of the tube. So we see that the wavelength is equal to 4 times the length of the tube. Again, we're going to use 0.6 meters as our tube length. We end up with a wavelength of 2.4 meters. So when we solve for that fundamental frequency, it's just going to be 142 hertz, all right? Look at the next possible situation. The next possible thing, if we have a node here at the fixed end, okay, the air cannot move there, all right? And instead we have a antinode at the other end, all right? We see we have 3/4 of our wavelength. When we solve for the wavelength, that length of the tube, all right, is in this equation gives us 4/3 that length of the tube is going to be the wavelength, all right? And an extra third, obviously, of the tube will give us a full wavelength. We solve for the fundamental, for the next frequency, we see it's 425 hertz. I've used f sub 3 right here because this is 3 times the fundamental frequency. So we see that we're going up by odd integers here with this example. Again, the length of the tube here is 5/4 of a wavelength. We see that this is one wavelength right here. We add an extra quarter of wavelength over here. So the wavelength itself is 4/5 the length of the tube, all right, which is 0.48 meters. We solve for the frequency, this harmonic frequency, it's 708 hertz, which is 5 times the fundamental harmonic frequency. Okay. So again, the displacement nodes, you have one node, all right, at the fixed end, all right, and one antinode at the free end. The fundamental frequency is when the length is equal to 1/4 of the wavelength of the wave that we're considering, and that frequency can be determined from this equation right here. And so for other natural frequencies, the frequency is equal to n times the fundamental frequency only if n is an odd integer. Okay, we see how it went up like that. All right, so these are the different examples of standing waves that we'll be dealing with in this class. We'll do some practice problems the next time. This standing wave right here, remember when I had the tuning fork held over the pipe, okay, the graduated cylinder? This is what this is an example of, okay? So pretty much all instruments are examples of these sorts of vibrations, whether it's a string instrument, okay, or a piano, the first example with a string fixed at both ends, or whether it's a pipe organ or some sort of wind instrument or even a brass instrument, right? Whether you have both ends being open or one end open, one end closed, all right? So that's it for now, and the next video is going to talk about interference.